My son's dog, Dish Soap, yes, that is his name, is afraid of boxes. Apparently, for dogs in New York City, this is not an uncommon fear. As an aside, New York City dogs are a special sort, and being a golden cavadoodle, every other dog in New York looks like Dish Soap's clone. Dish Soap is not in the forefront of thinkers of the canine world, but I think that makes this point even more clear. Why is Dish Soap afraid of boxes? Has he ever witnessed a box eat a dog? It seems to me that Dish Soap has assigned both agency and intentionality to the box. That is to say, in his worldview, in the model of the world he has constructed in his head, the box is capable of doing things, and the box may want to do something that would be unpleasant to Dish Soap. I think I can be fairly confident in saying that Dish Soap is afraid that the box will perform an action that would result in unpleasantness. If, in fact, this is what's going on in his head, and of course I'm open to reasonable alternatives, then Dish Soap must have at least some rudimentary sense of causality in the form of box, action, harm. We are susceptible to the same sort of cognitive biases, assigning agency where none exists, when we say this computer hates me, and assigning intentionality where there can be no intention. We even have a special word for it in our language, and that is anthropomorphism. I want to make it clear that I'm not discussing theory of mind in dogs or other animals. However, I am saying that the understanding of intention has generally been associated with higher cognitive function. Rather, I want to suggest the opposite. I hope to make the case that these cognitive biases, and others that I will discuss, are evidence of cognitive insufficiency in the face of the richness and complexity of the world. I'm Josh Young, and this is Playing Odd, a podcast about complexity and information in the natural world. Episode 11, The Crisis of Reality. It is impossible to conceptualize the complexity of the world in its completeness and depth, and we explored this idea when I discussed Laplace's demon. Instead, we say we focus on what matters. In the language of cognitive neuroscience and evolutionary psychology, we are decreasing our cognitive load to one that is workable. Thinking back to our very first episode in which we discussed compression in the genome and said that compression had to be lossless, we are dealing with a sort of compression here as well when we're trying to reduce the real-time calculations that would represent the world into a smaller set that is more manageable but is still sufficiently representative. In this case, we are going to employ lossy compression in that there will be some information that we simply discard. Some of this is obvious to us, as is illustrated in idioms like not getting lost in the weeds. But some of the compression is so ingrained that we no longer see it. And it is to this that I want to call our attention today. Now, in episode 11, we understand that changes and transitions like growth and the stock market and the weather represent evolutions of complex systems involving the interaction of a multitude of agents. We cannot point to a single agent or process it executes as being the cause of the transition of the system, but rather this transition occurs because of the interaction and interdependency of individual agents. However, sometimes a single agent is of such magnitude that its influences subsume those of all other agents. When a hunter shoots a deer, the influence of the agent that is the bullet on the complex system that is the deer is so overwhelming in magnitude that we can essentially ignore the contributions of all the other agents that make up the deer, the enzymes, and the biochemical substrates of episode 9. We can approximate the evolution of the system by simply saying the hunter killed the deer with a bullet, and this will be close enough to reality as not to matter. This construction of A causes B is what we call simple linear causality. The transition to a system as a result is what you and I call an event. We assign to this event a beginning and an end, and this description that takes place over a discrete amount of time is what we call a narrative. Linear causality can involve many steps, as in the case of the proverb, for want of a nail, the shoe was lost, for want of a shoe, the horse was lost, for want of a horse, the rider was lost, for want of a rider, the message was lost, etc. This chain of causality has many intermediary steps, but I want you to observe that it remains linear. This is quite distinct from the complex systems we've been describing in this podcast series. Neurodevelopment, although it evolves over time, is certainly not linear, or at the very least not serial. It is a highly parallel process involving many parts influencing each other over time, and, as such, is representative of what actually takes place in the world. In complex adaptive systems, unless the system truly collapses, there is no beginning or end. There is no possibility of narrative in the conventional sense. There is no simple causality. The construction of a narrative and the assignment of linear causality are approximations that we use to reduce our cognitive load. In some systems, as is the case with a deer, a single agent can be so overwhelming that the transition can be approximated with a narrative. But the fact that we recognize this as an event is, in a sense, the exception that proves the rule. We do not perceive the world as a series of constant and overlapping events, because if we did, the idea of event would have no meaning. Events are, by their nature, exceptional. It is not that nothing is happening between events. It is that what is happening does not lend itself to narrative or causality and can generally be ignored without imperiling us. The ideas of narrative and linear causality are expressed in other ways in our lives as well. Have you ever been so frustrated at your computer that you've wanted to yell at it? If you were to be asked about this impetus, you would certainly not suggest that you truly believe that the computer is out to get you. But why is this such a universal response? By assigning agency to the computer, we can construct linear causality that fits into our world model. The computer hates me and has made my life difficult. Again, I'm not suggesting that any of us believes that computers have agency, but these are such universal feelings that they represent a sort of cognitive bias. Would such a bias serve any selective advantage? Kurt Gray and Daniel Wegner wrote in their paper of 2010, "The embarrassment you feel hopping out of the water after mistaking a wave for a shark is nothing compared to the pain of having your leg eaten after mistaking a shark for a wave. The high cost of failing to detect agents and the low cost of wrongly detecting them has led researchers to suggest that people possess a hyperactive agent detection device." Such problems, like avoiding a predator, require rapid processing, and this sort of bias of simplification can be helpful. Indeed, suggestions of causal reasoning have been observed in corvids, a group of birds, as well as in other primates. The idea of causality requires some sort of model of the world, and presumably, for those corvids and other primates, the world model is not as sophisticated as ours, but it seems that some of the same shortcuts have been taken. All this goes to say that it is enormously difficult for us to internalize the idea of complexity. I certainly cannot do it. The approximation that is our understanding of causality is so ingrained that we no longer see it. Indeed, our language, the very words I speak right now, consist of subjects and verb phrases and themselves represent a description of linear causality. As a human being, I can imagine no other way. I do not know what a language of mutually influencing parallels would look like. These biases can, however, lead to problems of interpretation. When we say that smoking causes cancer, this simplification of a complex system is sufficiently accurate that we can incorporate it into our worldview. However, when we say that the latest weight loss fad will make us skinny, our biases towards linear causation do us a disservice. Even things like cancer risk by exposure to low-level radiation are difficult for us to interpret, and we talk of changing probabilities of cancer rather than of certainties. But what do these probabilities mean? Does it mean that there are stochastic elements involved? Certainly this is the case. But I would put forth that even if there were no stochastic elements, even if we ourselves were entirely deterministic, there would still be no certainties, only probabilities. This is akin to the deterministic chaotic systems that we saw in which the outcome was unpredictable even though all the rules of the elements were known. Each of us is a slightly different complex system, and these subtleties, these initial conditions, make forecasting difficult and sometimes even impossible. I am a scientist, and I say without equivocation that science is the means by which we will gain understanding of the universe. But I do want to point out the influence of narrative and causal biases in the scientific method. In science, we make observations and form hypotheses which we then test. The difficulty is that many of these hypotheses have their own narrative biases. It is rarely the case in biology that A causes B. Better it is to understand that A influences the system in a way that makes B more likely. The difference is not semantic, but genuinely conceptual, and it is difficult. How might we move forward as scientists with our understanding of complexity? One model might be one influenced by the approach of physicists. One area in which multiple interacting agents influence the state of a larger system is the field of quantum field theory. Now, before I go any further, I'm not suggesting that any of the systems that I have described are quantum, and I'm not going to explore the role of quantum physics in neurology. I am merely presenting the conceptual framework of quantum field theory as an example of a highly parallel interactive systems. When we speak of fields in physics, we're talking about particular properties that are distributed over space. One example with which we are all familiar is of magnetic fields. In quantum field theory, the fields are influenced by the presence of particles such as photons and electrons. Before my physicist friends tune out, I know that my last sentence is untrue, and I will revisit it in a few minutes. Each of these particles has properties, and the particles interact with each other according to their properties. This is beginning to sound very generally like our description of complex systems. In the case of electromagnetism, two particles interact by exchanging a particle that represents the electromagnetic force, in this case, a photon. The classic analogy is of two skaters on an ice rink throwing a ball back and forth, and the ball itself conducts some of the momentum from skater 1 to skater 2. In a similar way, the photon is a vehicle for the electromagnetic force between two particles. In truth, quantum field theory does not view these agents as discrete, but rather views all of this as features within a single quantum field. The electrons themselves are probabilistic perturbations of the field, but the view is much more holistic. The field itself evolves over time according to Schrödinger's equation. The complex biological systems we've discussed in this podcast are analogous to the field, and in the same way that the quantum field is adaptive to perturbations from electrons and other particles, our complex biological systems are adaptive to environmental influences. So far, so good. Carlo Rovelli, a physicist and author with special interest in loop quantum gravity, describes objects in the field, and to some extent all objects, as collections of properties that describe the nature of the interactions they have with other particles. To Rovelli, the electron is not so much a discrete physical object, but is rather defined by what it does in relation to other particles. The idea that something is what it does is another example of describing the elements of a system by defining the system as process rather than product, one of the chief themes of this podcast. In the case of rennet and cheese making, of a chess piece in the game of chess, or indeed of the little machines we call proteins, What is important to the system as a whole is what these agents do and not what they are made of. If an enzyme were swapped out of the system for something else, let's say a bit of nanotechnology that had identical properties, the system as a whole would not change at all. In this way, the methods of quantum field theory can serve as a guide for us in interpreting complex systems in the macro world. There are problems with this approach. All electrons are the same. In biological systems, individual agents are often different from each other, and these differences introduce important stochastic elements that are absent in quantum field theory. This is, of course, not to say that quantum field theory does not have stochastic elements, but if you've seen one electron, you've seen them all. There is a small literature in the application of field theory to complex systems, and this may be a fruitful approach going forward. In this episode, we have discussed the impossibility of incorporating the richness and complexity of the world into a cognitive model that we can fit within our limited cognitive resources. We discussed the ways in which evolution seems to have reduced cognitive load by producing simple models that are approximations of reality. We saw how these approximations lead to biases of agency and intentionality and a bias towards understanding the world in terms of narrative and linear causality. We observed that other fields within science have had analogous challenges and have met them with a holistic approach, such as in the case of quantum field theory. We have seen that our quite understandable difficulty in conceptualizing the tremendous parallelism and simultaneity of reality has shaped the model of the world that we hold in our brain. But what does this mean for brains that we build? What are the implications for artificial intelligence? This will be the subject of the 12th and final episode of this podcast, and I look forward to discussing this incredible subject with you next week. Talk to you then. I'm Josh Young.